that will not cause me to be taking the log of a negative. So I go back and I look at my log expression. If I put 4095 in there, there's no way that's negative. So this is a valid answer. We move on. Let's take a look at the second exponential problem. This one says solve y equals 2.1 e to the kx for k. And we got the given information that x is 4 when y is 12. Well, we need to use that given information, so I'm going to write that into the equation. When y is 12, so we'll have a 12 on the left, x is 4, so we'll say 2.1 e to the 4k because x is 4. Well, that's an exponential equation because k, the variable we're looking for, is in the exponent. So in order to solve that, we need to isolate the exponential. Now only this part is the exponential. The 2.1 is to the 1 power. It's not to the 4k power. Only the e to the 4k is the exponential. We've got to get that by itself, so I'm going to divide both sides by 2.1. On the left side, on the right side now, the 2.1 is gone. So I'm just left with e to the 4k is equal to 12 over 2.1. Now 12 over 2.1 is just a number. You could just pop that into your calculator. But we've done step 1. We've isolated the exponential, and now it's time to take logs of both sides. This time the choice of log is pretty obvious, since the exponential is base e. And since log base e is on your calculator, that's what ln is. You want to take ln of both sides, so that's what I do. ln of e to the 4k, and make sure you show this step, is equal to ln of 12 over 2.1. A lot of people get sloppy here, and they end up with something like ln of e to the 4k is equal to 12 over 2.1. It's not. You're taking the log of both sides. The ln of e to the 4k is the ln of 12 over 2.1. Well, the ln and e to the x reverse each other, so the left side is just 4k. And on the right side, there are no variables, so this is just a number that can be punched up in your calculator. And to finish this problem, you divide both sides by 4. And if you want to see what that looks like going into a graphing calculator, the graphing calculators are available at test time. If you want to see what that looks like going into a graphing calculator, there's only one number on the top, so I don't need a bracket around the top. It wouldn't hurt to put it there. If you feel better putting a bracket around the top, go ahead and do it. It won't hurt a thing. But that's what you need to put into your calculator, and I'm going to go ahead and put that in exactly as I've written it. Now always write it out first. Don't try to go straight into a calculator. Write it on your paper in proper form. Then put it in your calculator, or you are just asking for trouble. I hit ln open 12 divided by 2.1 close divided by 4. Enter, and I get 0.4357, so I'm going to change it to 0.436. So I'll say this is approximately equal to 0.436. Let's take a look at our last log equation. Here we have two logs, and I have trouble isolating a log. I mean, I can isolate the log on the left, but the right, but the log on the left is not isolated. If I move the 5 to the other side, the left log will be isolated, but the right one won't be. This is kind of a problem for me, so what I'm going to do instead is move both logs to the same side and the 5 to the other side. Then I'll use the log properties to make a single log on one side. So let's get started. I'll bring the log 2 over to the left. So I'll have log 2 of x minus 3 minus the one that I'm bringing over, log 2 of x minus 2, and then I move the 5 to the right. Negative 5 becomes positive 5, so that's equal to 5. Now on the left, I now have the difference of logs. The rule says the difference of logs is the log of a quotient. So I'll rewrite this as a single log of the quotient x minus 3 over x minus 2. Again, the parentheses are very important, and that is equal to 5. And I have now successfully isolated a single log on one side. And the rule says isolate the log, then change to exponential form. Well, if I read from the right to the left, it says 5 is the log 2, the exponent of 2. 5 is the exponent of 2, so I write that. And it's the exponent of 2 that gives me x minus 3 over x minus 2. Well, that's two terms. Common denominator is x minus 2, so multiply each term by the common denominator. And 2 to the 5th is just 32, so I get 32x minus 64 is equal to x minus 3. I take the x to the left, so that'll leave me 31x. I take the negative 64 to the right, where it becomes positive 64, so I get 61. I divide both sides by 31. And this looks like a perfectly legitimate answer. It's a nice positive number. It's a little bit less than 2. It's 1 and 31st, just a hair smaller than 2. But to be sure that the answer is legitimate, I have to go back to the original equation and make sure that that doesn't have me taking the log of a negative number, which would be undefined. So I go back into the first log, and it says the log of x minus 3. Well, this number's less than 3. So if I subtract 3, I'm going to get a negative. Therefore, I have to throw that answer out and say no solution. And that ends our first session on solving exponential and logarithmic equations. I'll now have 2 or 3 more exponential examples and 2 or 3 more logarithmic examples.